So welcome everyone to the N2O Notes Webinar Series. This is part 2 of the series, where we're going to be covering measuring and reducing N2O. Last week we covered accounting for and assessing N2O wastewater and process emissions. And we're going to be continuing here. But first we get into measuring and reducing N2O, I want to give a brief recap of the N2O reduction journey. So the N2O reduction journey starts with what we covered last week, accounting for and assessing N2O. We want to be doing this because we want to know where we need to be prioritizing action, where we need to be focusing action. So we can be screening sites, and depending on what sites have higher N2O emissions and what sites have greater opportunities for reducing N2O, these are the sites we want to be prioritizing to then be able to go and measure and reduce N2O. So with the counting, we were able to predict what the N2O emissions are, much better than using generic emission factors, which are not capable of accurately estimating the actual N2O emissions because they don't account for the site-specific conditions. But we can with machine learning. So we're using machine learning, our machine learning model library, to account for the N2O emissions, see which sites have higher N2O emissions, and then we use the knowledge-based AI. We can start looking at the risk of N2O to see what sites have greater opportunities to reduce N2O. So once we've identified those sites, we can then go and measure and reduce N2O. Which is what we're going to be covering today. Once we've measured and reduced our N2O, the journey doesn't end there. The work continues because we want to keep our N2O emissions down. We have to be monitoring the process. And N2O. So if we see N2O emissions going up, we know what to do to bring them back down, because any reductions that we're able to achieve today, they can easily go away with changes in the process, changes in the loading conditions. So if we're not continuously monitoring the process and continuously making adjustments to reduce N2O, our N2O emissions can increase. And if the goal is to reach net zero, we don't want to reach net zero and then forget about everything. We want to stay net zero. So I think that in order to stay net zero, it's important to be monitoring the process and monitoring N2O, so that we can continuously be reducing N2O and continuously be minimizing N2O. But again, today, we're going to be focusing on measuring and reducing N2O. So one thing that's going to be important to keep in mind are the N2O dynamics, because this is going to be important for determining where we need to be measuring N2O within the wastewater treatment plant. Because if we don't understand at least some of the basics behind the N2O dynamics in terms of the pathways and the influencing factors or risk factors, or what could be considered root causes, We ultimately want to know why we have N2O emissions and what we can do to reduce those emissions. And to do that, we can simply be looking at the operational data, because we can be producing N2O at each step in both the nitrification process and the denitrification process. And what happens at the metabolic level is what dictates whether we have N2O emissions or not. But we can't see what is happening at the metabolic level. We can only see what's happening on an operational level. And through the research, these operational conditions or influencing factors have been directly linked to risk of producing N2O, because they directly impact what's happening at a metabolic level. So we can have N2O in nitrification, we can have N2O emissions due to high DO conditions, but we can also have N2O emissions due to low DO conditions. Nitrate is another big factor in denitrification. There's certain conditions that will lead to accumulation of N2O and emission of N2O, as opposed to conversion of N2O to nitrogen gas as an intermediate in the denitrification process. So if we don't have a framework to be able to be looking at any combination of these process conditions or operational conditions, and at each site, and within each site, each reactor, and within each reactor, each zone, then it's going to be very difficult to understand what the total emissions are and what we're going to be able to do to reduce those emissions. But that we have built that framework, and based on the knowledge from the research and the linkages between the operational condition and process conditions to risk of N2O, we can use AI techniques to generate a dynamic risk score. With every data point, we can generate a risk score, and we can also categorize that risk in terms of the individual risk factors or influencing factors. So we know why there is risk, how much is that risk, whether it's 1, which is very high, or closer to 0, which is very low, and what we can do to reduce that risk. But we also use machine learning to predict what the actual emissions are. So what we're combining is a knowledge-based approach with the data-driven approach, and the machine learning is more of a black box, because if we see N2O emissions going up, it's based on strictly predictions using correlations in the operational conditions and using data. We're not going to know why that's going up. But if we use the knowledge-based AI, we can know, because we could also, as N2O is going up and down, we're going to see risk going up and down, and that's going to tell us why N2O emissions are going up and what we can do to bring them back down. And that's what we implement within our N2O risk DSS platform, which helps us go through each part of the N2O reduction journey in terms of accounting for and assessing N2O, reducing N2O, and monitoring N2O. So last week we covered accounting for and assessing N2O, where we're gone through the process to account for N2O at various sites, and have been able to see what the N2O emissions are, what the risk profile looks like, and what opportunities there are for reducing N2O. And this is an example of what Waterboard de Dommel in the Netherlands is going through. So once we've able to have done this, been able to do this for a number of sites, we can now identify what sites we want to go measure, and that's what we're picking up from this week. So why we want to be measuring and reducing N2O first starts with verification. So we want to be measuring because we want to verify current emissions. And risk. Because if we're using risk to assess our N2O, which we have actually have validated very robustly, looking at over 30 sites in various conditions all over the world. So we have a lot of confidence in the risk, but it's always nice to see the risk correlate to actual N2O measurements, because then we can have even more confidence in using the risk to monitor the process going forward. So first, we want to be verifying what the current emissions are, because at this point, we've been using our machine learning model library, which can give us very good results and fairly accurate numbers. But those are models, and even though we have over 50 models in the library with varying process conditions that can be matched to your process conditions, they're still not going to be perfect. There's no perfect model out there. So it is always going to be good to verify what the actual emissions are with physical measurements. The other reason we want to be measuring and reducing is because we want to verify what the reduction is. So if we're measuring before we implement recommended control actions, we get to see what the current emissions are. But then if we continue to measure, then we can measure after implementing recommended control actions, and then we'll be able to verify what the reduction is based on physical measurements. And this is actually how we assess our greenhouse gas reduction fee, based on the difference in the physical measurements between before and after implementing recommended control actions from the platform. Because we feel that people are always going to prefer to base a fee based on what is physically measured, as opposed to what might be modeled using the historical data. But we're quite flexible on that, because if you're looking at a whole year of historical data and using the machine learning model that you might be training with your measurements at this specific site, at a specific site, then theoretically you can look at the whole year before, account for the seasonal variation, and base your current emissions on that. And then based on what you reduce, you could assess the fee that way. If we have a customer who feels more comfortable doing that, we're happy to do it. But we're tend to think that basing the fee on physical measurements is better, at least for now. So the other reason why you want to be measuring is because we can train a machine learning model. Oops. Go on ahead. For monitoring. So we have the, now if we have our measurements, we can train a machine learning model, because we don't always have the luxury of physically measuring and continuously measuring N2O indefinitely. That can be costly due to the maintenance, which we'll be discussing. So in lieu of continuous physical measurements, we can use a machine learning model after a period of measurements to then be monitoring the N2O emissions after reducing N2O. So the other reason why we want to be measuring, because then we can train this model and then leverage that model to look at the historical data. So with the trained machine learning model for the site and with the historical data, we can then see what the seasonal variation might be in the N2O emissions. We don't have to measure for a full year to see what the seasonal variation might be in the N2O emissions. There's a misconception out there that some people think that you have to measure for a full year before you can reduce N2O so that you can see what the actual emissions are, taking the seasonal variation into account. And I think at this point, given the climate crisis, the climate disasters that we're seeing, to allow, if we're measuring and have the capability to reduce N2O emissions, but rather just allow the N2O emissions to continue to be released for a full year, just to see the seasonal variation is irresponsible at this point. We can use our tools. If we want to see seasonal variation, we can use our tools and use the historical data to do that. And instead, instead of measuring for a full year without doing anything, we can be reducing our N2O. We can, if we want to measure for a full year, we can, but instead of measuring for a full year to see the seasonal variation, we can be measuring for a full year to verify that we can maintain the N2O reductions. So if we're going to be measuring for a full year, that's why we should be doing it, not to see the seasonal variation. And the overarching reason why we want to be measuring and reducing N2O is because I'm having trouble. It gets us closer to net zero. The only way we can get to net zero is by reducing tons of CO2 equivalents. So if we're going to be needing to reduce tons of CO2 equivalents, we should be reducing N2O, because it's actually the easiest, fastest, most cost-effective, and most impactful greenhouse gas for water utilities to reduce. So this is why we want to be measuring and reducing N2O. So for measuring N2O, there's various methods, and which method we use will depend on, or what is the best method to use will depend on what your situation is, because there's pros and cons, and based on what your objectives are, what your resource availability is, and based on your budget, you may select one method versus another. So we'll go through each of the different methods. We also need to know where to measure. So we'll discuss where to measure, be able to getting they're able to get representative measurements, and we'll also discuss for how long to measure. So I want to remind people that we have this book that we recently launched from the IWA task group on greenhouse gas modeling. And there's a chapter in the book dedicated to full-scale quantification of N2O and methane emissions. So I highly recommend downloading this book. It's free to download through open access. And there has been, in all of the chapters, entire book, there's been some really bright people contributing to the book. So it's an excellent resource to have. Highly recommend it. But covers a lot on actual measurements, so it's worth taking a look. So in terms of the different methods for measuring N2O, we have floating hood method, we have liquid phase measurements that we can do with a sensor, there's mobile trace dispersion methods, and there's other methods like getting grab samples and then monitoring them back at the lab with the GC. And there's a less drone, which is kind of like a hovercraft that can hover over the water surface and get measurements. And this was developed through the LessWatt project, which we were involved in. And we have experience with each of these methods, except for the mobile trace dispersion method, but we have good contacts there because it can be a useful method. And there's some people out there that can do a really good job with this. Explicit is one out of Denmark. D2U, also in Denmark, can do this. And there's also a group out of Princeton University has been doing this. So that is a good another possible method. We'll go through each one of these and discuss some of the pros and cons. So for the floating hood method, that involves a hood that floats on the water surface, like this one here. And there's different types of hoods. And we've put them side by side, like we see here. And this is like a flux chamber. So this is available commercially. This was constructed actually at people at Biomath at Ghent University through a project working with Waterboard de Dommel. And we've even made homemade ones too, which can be made fairly cheaply, just getting materials from the hardware store. And in the end, what we've been seeing is that there really isn't any significant difference between hood types. What is different is, I guess, the area that they cover. So with the larger hood, you can cover a greater area, but it's harder to move around. And we want to be able to move around the hoods because we want to be verifying not only what differences there might be longitudinally through a reactor, because depending on the mixing conditions, if they're plug flow conditions, you can have higher concentrations of ammonia, different concentrations of dissolved oxygen, which will lead to different concentrations of N2O and different emissions of N2O. So you want to be measuring if there are changes or gradients expected based on the process, then you want to be measuring where you have different concentrations so you can get a picture of how the N2O emissions. So normally we have higher loading, higher ammonia concentrations, you're going to have higher emissions. But it also depends if that zone is operated differently than in other zones. So it's good to be looking at the data, looking at the risk, in addition to be measuring in different locations so we can verify that if there's any spatial variation longitudinally. But laterally, there could also be differences due to different mixing conditions. And normally, if it's a narrow channel and it's well mixed, there shouldn't be any significant differences. It's when the channel starts to get wider and there then the possibility for different mixing local conditions can be greater. But that's why we can be spot checking. We can move the hoods around to check to verify that. The other part of the floating hood method is the gas analyzer. So here's a picture of an analyzer. So you would have air tubing connected to the hood. It has to be airtight, which would bring the sample to the analyzer where we're able to measure the concentrations of different gases. So depending on the analyzer, not only might you be able to measure N2O, but you can also measure, depending on the analyzer, also methane, CO2, oxygen. But obviously we're interested in the N2O. So here we can get our N2O measurements. But as you can see, there's quite a bit of equipment involved. You also have gas cylinders you might have to be transporting for calibrating the analyzer. One thing you also have to be careful of is you have rope tying the hood, securing the hood. You need to leave enough slack in the rope especially if there's possible changes in water level. So if the water level can change significantly based on the incoming flow, you want the hood to be able to move up and down with the water level. Because if you don't have enough slack, what can happen is that the water level will change, but the hood won't. The position of the hood won't. It won't go up or down with the water level. So that can mean that either A, it goes below the hood, and then you're just sampling the ambient air, or the hood can stay below the water, and at that point you start to suck in water, which can cause big problems with the analyzer. And some analyzers have built-in system moisture trap, where if it does start to suck in water, it'll shut it down. That prevents sludge from going into the analyzer, which has happened to me. And that's not fun, because then you have to take the analyzer completely apart, clean it, and then put it back together and cross your fingers that it's going to work again. And luckily, have been able to get it to work again without any problems. And it was actually lent an analyzer to me one time, and was told that, yeah, I don't have to worry about paying for it. There's no rental fee, but if it breaks, then you have to pay for it. So I was really nervous when putting it back together. Thought that I was going to have to pay like $20,000, but luckily I didn't, and had great support actually from the manufacturer. So that's the floating hood method. Has its pros and cons, very accurate. Measuring directly what the emission is, you don't have to calculate it, but you also don't know what is happening in the liquid, in the water, in terms of production. But generally what we've seen when we've measured in the liquid and in the off gas simultaneously, side by side, that the production matches the peaks in the liquid phase, match the peaks in the off gas concentrations. So it can tell you, actually can tell you what's going on production wise. But it also depends on the situation, because you could also have non-aerated a zone upstream from here where N2O can be produced, but it won't be emitted until it gets here. So if you do measure something in the off gas, you're not going to know how much is from the actual production here and how much is from the upstream anoxic zone. But we do have the tools to also tell us. We have the machine learning, we have the risk to tell us whether we should have production here, whether production is predicted here, and whether it also is produced upstream in the anoxic zone. So we talked about doing measurements in the liquid, and this is with Clark type sensor, which is manufactured by Unisense out of Denmark. So this involves just having a controller here and the sensor. So this is a sensor body. There's sensor tips that go inside of it are protected here. And this tends to be a bit easier to use. It tends to be our go-to solution for getting measurements because it's easier to move around from site to site. It's easier to move around for checking different locations to see if there's any spatial variation. And it's fairly quick to get going. It's easy to, the calibration is pretty straightforward, although you have to be paying attention to what you're doing because it can be a little tricky, especially uh, if we've learned the hard way that you can get a bad calibration with the calibration solution is not at the same temperature as the wastewater. So you need to be making sure that it's the same temperature as the wastewater. But as long as you follow the recommended procedure, you can get going fairly quickly and can be getting fairly reliable results. So the other thing that I guess to know about this is that the sensors themselves, they only last 4 months or sometimes a little longer. So you are going to be needing to be replacing these. So that's one disadvantage because that can drive up the cost. And if there's any significant change in the temperature of the wastewater, you're going to have to be calibrating. So depending on how fast the temperatures change, it'll dictate how often you're going to be needing to calibrate the sensor. The sensor also is measuring the N2O in the liquid. It's not telling you what the emission actually is, but with the airflow data from the plant, we can calculate what the emissions are using mass transfer equations and assumptions in terms of mass transfer coefficients, what the KLA value is for N2O. And if those assumptions aren't quite correct, you could have some error in what emissions you're actually calculating. But this doesn't generally tend to be very much. I think Unisense says that it's somewhere in the range of 10 to 15% at times. But the good thing is that that can easily be corrected with measuring in the off gas simultaneously for a period of time. And then with that data, the emission data, you can correct the KLA and then get much more accurate, more reliable calculation of what the emissions are. In terms of the mobile trace dispersion method, this involves driving around the site and taking the wind direction, atmospheric conditions into account, and capturing a plume of the N2O or methane. Methane can also be measured. The problem is that this is only a snapshot of what the emissions are. It's only capturing one moment in time. So it's not able to capture the dynamics. It's also not able to tell you what's happening on a reactor level and on a zone level, which makes it difficult to understand how you can reduce N2O. But the good thing is that it can also be a good thing because now you don't have to measure in each of the reactors and in each of the zones because you're capturing emission for the whole site. So it makes it a little easier in that sense. But the other thing is what we can do is combine our tools. So we can be calculating or predicting what the N2O emissions are in each of the reactors, and then be using mobile trace dispersion measurements to verify that the total from each of the reactors equals what is actually measured for the whole site for the same period in time. So this does have a place in our N2O reduction journey. But again, it really is going to come down to budget, what your goals are, what resources you have in terms of what method you're going to be using. And here's a summary of notes. Save you the time and waiting for me to write each of these. So I was just typing them, so just type them. But we see that different methods can be used. Each method has its pros and cons. There's practical considerations that need to be taken into account when selecting a method. It's important to use the method that's best for you and helps best meet your objectives. And the good thing is that our N2O risk DSS can leverage N2O data collected with any of these methods. Okay. So in terms of where to measure N2O, this is where process knowledge becomes important, because if you don't have process knowledge, then you're not going to be able to understand where you can be measuring N2O. On the other hand, if you don't have knowledge on N2O dynamics, you're also not going to understand where to measure N2O. So you really need both. You need the process knowledge and you need the N2O knowledge. Because as I mentioned, depending on your loading conditions, you generally will tend to have higher emissions where you have higher loading and higher concentrations of ammonia. So if you have plug flow conditions, like in this particular example, you want to be making sure you're measuring in the beginning of the lane, but also towards the end to get the full picture. Because if you have lower concentrations, and assuming you're operating at similar risk, you're going to have lower emissions. So you can't measure here and assume that what you're measuring here is the case for the whole entire lane. So you need to be thinking about how you can break up the lane into areas where you measure to then be able to assume that the emissions measured are the case in the different parts. So need to be thinking about that for longitudinally, like I mentioned before, and also laterally, you need to be looking at the width of the channel. You can look at the mixing. You can look for any dead zones. Dead zones would be a dead giveaway that you can have significantly different emissions across the reactor. But if the channel's narrow, I think generally that tends to be less of a concern. But the good thing is that we can be checking, as I mentioned. So in this particular example, knowing that the lane is broken up into two zones, measuring in the middle of each zone would be reasonable, because what you measure here, and if you're able to verify that in different locations, the emissions don't vary significantly, then you know you're good to go with measuring this location and assuming that this whole area has the same rate of emissions. But as I mentioned before, it's important to check. So we can check to see that there aren't any significant differences in what is measured up here versus here, and also across the reactor. Because if we do see that there's any significant differences in any of these locations, and we know we're going to be measuring here at least for some time, we can develop a machine learning model for these other locations based on what is measured at the location, at our reference location. And then once we're done with those measurements, we can predict what the emissions are here based on what is predicted here if we're using machine learning to monitor the process after measuring. The other good thing is that if what we measure here, if we train a machine learning model here, we can get more out of our measurements by using that machine learning model to then predict what the emissions are in the parallel lanes. Because it's not feasible that we're going to be able to put sensors in every lane and in every zone. It's just not feasible from a cost perspective. But we can use this machine learning model to then take into account the lane specific conditions. Generally, they operate the same, but we know that there's never perfect air distribution. We know that the DO concentrations aren't exactly the same, and slight differences in the operating conditions between one lane versus another can have a big impact on the N2O. So we can't just assume what we measure here is the same in the other lanes. So we can take into account the process conditions in the other lanes to predict what the N2O emissions are and monitor the N2O that way using the machine learning model that was trained on data from where we did measure. So in terms of where to measure, we need to be considering the flow regime, nutrient concentration gradients, loading, N2O pathways, and the dynamics. We need to be checking multiple locations with the sensor or the hoods, using a reference point to check if there are localized differences within the reactor. And we can get more out of our measurements with machine learning to predict N2O in other locations if there's any differences seen in the spot checks, and to predict what the emissions are in the other lanes by taking into the process conditions into account in those other lanes. And in terms of how long to measure, so we talked about this earlier, we don't need to measure for a full year to understand what the seasonal variation is. We typically recommend doing 1 month of measurements, and once we're doing that, we can train a machine learning model. We can see how accurate it can be using that 1 month training data. And in that month, the first 2 weeks can be before implementing the recommended control actions, because then you get a period with higher N2O emissions. And then you can also continue to measure for an additional 2 weeks after implementing the control actions, because then you get data to train your model with lower N2O emissions. And then going forward, you're going to have a model that is able to predict higher N2O emissions and lower N2O emissions. So you can use it to monitor what your N2O emissions are. So because you'll be able to predict if they're going up or if they're going down, and you can use the knowledge-based AI to tell you why they're going up and why they're going down, and what you need to bring them back down if they're going up. So we've actually been testing this approach because we've had the luxury of having a number of N2O data sets, field measurements. So we tested training this model in January. We went back in time to then apply that model with the historical data. And then here we can see what those predictions are. We can see that there's variations. You can see during the warmer parts of the year, we see slightly higher emissions, and this is quite typical. Tend to see this a lot, and this is a function of just having higher activity with the higher temperatures. And the key there is that you don't want higher activity with high risk. So you have higher activity with high risk, you're gonna have higher N2O emissions, and that's what we typically see. But we can test this. So using the measured N2O, we can compare it to the predicted N2O from with the machine learning model trained on the 1 month of data. And what we want to be looking for is that the predicted N2O is capturing the dynamics, because we can't expect it to be perfect You can see that for some of these peaks, it's not quite getting the full magnitude of these peaks. Uh, but because these are very short periods of time, and because it is capturing the dynamics, and for most of the time it's capturing these dynamics, it is able to accurately predict what the emissions are. And it is able to predict when the N2O is going up and when the N2O is going back down. But if we're using this data to calculate the emissions, and based on the measured data and then based on the predicted N2O, we can see that it actually comes very close. It's like 292 versus 289. So for the purposes of looking at the historical data to see how the variation, seasonal variation is and how N2O might change as the process is changing, we can consider this to be very good. And the other surprising thing is that we trained this model with data from January. You can see the months here. This is July and August. So we can see that it can be quite robust. And this isn't going to be the case for every case. In some cases, we're going to see that a winter model is not good when we've seen it, is not good in the summer months. So we need to really be taking these things into consideration. The other good thing is that we can also look at the risk and see if the predicted emissions are making sense with the risk. So in terms of how long to be measuring, we need to be measuring long enough to capture the dynamics. And normally, because the loading, the flow, and the loading conditions tend to be pretty consistent for a treatment plant, normally if you're measuring 1 or 2 weeks, you can capture this, but we recommend a month. And then we also recommend going back. So we want to verify the machine learning model accuracy. If we're using it to monitor the N2O, after reducing N2O, by going back and having shorter measurement campaigns, like 1 week, to verify the model, see if it's not accurate, we can retrain it with that data. But the other thing that we can be doing is if we see that the process in between measurements, if we see that the process has changed to the point where we're not confident in the model, then we can look to the machine learning model library to pick a model that would be more accurate based on the process conditions. So I think for monitoring purposes, we have a pretty robust solution if you're planning on going back and measuring. I think good practice is to be measuring 2 or 3 times throughout the year, and at least for the initial year, because we will probably find that over time you might reach a point where the model's robust enough because you've collected enough data that you won't need to be going back to verify the model. But if obviously if the process is changing, then maybe that would be needed. And we can also see that once we've trained the model, we can go back and look at the historical data to look at the seasonal and operational conditions. So if we want to not measure for a full year, which we shouldn't, to understand what the baseline conditions are, we can use the machine learning model and the historical data to understand that. Now for reducing N2O, probably thought it'd be easier to just do a live demo. So let me stop sharing here and go to our platform. So here we have a data set where we can pretend we have not gone and measured yet, but we have gone through the accounting of N2O and our assessment of N2O in terms of the risk and the opportunities to reduce N2O. And in this particular case, we saw risk due to high DO conditions, which is the red peaks here, and risk due to low DO conditions, which is the blue peaks here. And we've looked at the dissolved oxygen. So this is what the dissolved oxygen looks like. And we've assessed what the recommended dissolved oxygen is based on what their current dissolved oxygen is and what their risk is. So we look at the dissolved oxygen and the risk to then be able to recommend what the dissolved oxygen is. And you can see the DO was above and below the cyan line, the recommended DO, quite consistently. So you see it when there's the red, you see it above the blue line. When there's blue, these peaks in low DO risk, it's because the DO is below the blue line. So we're recommending to them that they fine tune the control, because they actually have a ammonia-based aeration control. So we don't want them to change the control. We never really want them to change the control. We just want them to fine tune it so that they can still do what they're currently doing, but fine tune it so that they can come closer to the cyan line. Because the idea is that by doing that, they're reducing the risk and reducing the N2O emissions. So if we look at, so based on this, we have identified this site as a site that we want to go and measure. So the next step would be the actual measurements. So we've collected the N2O data. We can pretend we collected the N2O data. Then we want to use that to verify what the actual emissions are. So here we're getting to see what the N2O was measured. And we can see that it is correlating with the risk, which we tend to see. So here, see it correlating with these peaks in the low DO risk and these peaks in the high DO risk. Here we can see a big one here happening during this period of high DO risk. Again, we see it going back up with the low DO risk and going back up with the high DO risk. So this tells us that if we're using the risk to monitor the process, we can have confidence in this. And we see this every time, but it's just nice to verify it with physical measurements. It's always nice to verify with physical measurements. So taking the DO and the recommended DO into account, we want to see how bringing this closer to the cyan line, what impact that has. So they can actually, we can see what that effect is. So they actually made this change after this point here. So if we can extend this out to show the days where they implemented the control actions, we can now see that the DO came a lot closer to the cyan line, almost came perfectly in line with it. And we can see that now their N2O is down here, where before it was all the way up here. And we can see, so I guess the other interesting thing to look at is the ammonia. So we see, so the ammonia was looking like this before, and now it's kind of a lot more stable here. It doesn't go above this point. And that's really a function of fine tuning the process. So now before they were allowing the DO to go all the way down here. and then they would have to be bringing it back up. Um, and because they would keep it down low, they're allowing the ammonia to increase to a certain point. But by keeping a tighter band in the control and the range of the DO, they can keep a tighter band in the ammonia concentrations. So now they're not converting these large peaks. Like here's a perfect example. You don't want to see ammonia conversion underneath a peak of risk, because if you do, then you're going to see a peak of N2O. So now you're still converting ammonia, obviously, because you have to, but now you're doing it under lower risk. You can see the risk is way down here, where before it was way up here. So now, because we've been able to reduce that, we've been able to knock down the N2O. So you can convert ammonia at lower risk and not produce as much N2O, almost eliminate it. And there's some methods that try to consider the ammonia conversion. So here, if you look at the effluent ammonia, on average, it's not going to be much different than it is here, even though the range in ammonia is high. It's still bringing it down to the same level. It's just that it's not going up as high. And actually, before they were bringing it down lower than they are now. So if we can see that's a little bit clearer. So they're bringing it down. So on average, if you're looking at the effluent, so now they're not bringing it down as far, but they're not allowing it to go up as high. So if you're looking at how much ammonia is converted, you're going to see the same, roughly the same. But there's some methods that say if the lower your ammonia conversion, the more ammonia you're converting, the less N2O emissions you're going to have, and that's not necessarily true. So you can't just look at what's going in, what's going out. You have to look at what's happening inside the reactor to really understand whether you're going to have higher or lower N2O emissions. And in this particular case, they're able to reduce the N2O by 90%. And because N2O made up such a big part of their total emissions for the treatment plant, they were able to reduce the total by 70%. So here we can see a perfect example of making a big impact by reducing N2O. And they actually, because they were over aerating for periods of time, so now they're keeping the N2O, or sorry, the DO closer to this blue line. They're not over aerating. So they're not allowing the DO to go as low, but they're also not allowing the DO to go as high. So they also had a net reduction in the energy consumption. It wasn't a big reduction, but there was a reduction in the energy consumption. So it was a win-win in the situation. And there was a question whether biogenic CO2 emissions can be added to the AI graphs. And theoretically, yeah, there could be. But in the methodologies and the theory behind is that the biogenics don't contribute to net increase in global warming. So they're generally not accounted for in greenhouse gas accounting methodologies. But the other thing that you'd have to be doing is be looking at the other process parameters and then also be calculating what those would be. And so if you have the data, then you'd be able to do that. But right now, we can't click one of these buttons and automatically give you the biogenic CO2 emissions, but it is possible. So stop here, we'll go back to the presentation. We can look at a quick case study for Welsh Water, and where they followed the same approach. They looked at the risk, they looked at their emissions. They saw that there's opportunities to reduce. They were able to verify that the N2O was following the risk. They had these big peaks in N2O happening underneath, N2O increasing underneath these peaks in the risk. So the obvious control action would be to increase the DO. All of this time that it's below the cyan line, we can increase it. And what they were actually doing, they weren't making a change in the control because they couldn't. They were maxed out with their blowers. But what they were doing was replacing diffusers. And by doing that, they were able to get the DO up, because now they were getting much better oxygen transfer efficiency because the diffusers were old and fouled. So that essentially gave them more capacity. Even though they didn't increase their blower capacity, they were able to increase their oxygen transfer efficiency, and that allowed the DO to come up. And we saw that that had an immediate impact on the N2O emissions. In fact, that now we see a lot more red, but we see shorter periods of the red compared to like these long periods of just having low DO risk. And there's even a little bit of this low DO risk still, but it's much shorter. So you can see this N2O peak going up right underneath this peak in the low DO risk. But they've been able to reduce that significantly as compared to how it was previously. And that actually resulted in a reduction of 82% of the N2O. And so that was a nice example where if there are planned improvements at a treatment plant, how they might help. So this is another thing that to take into consideration as you're screening and prioritizing sites where you want to go measure. Because if you know that there's going to be improvements made at a particular site, and you know that depending on what improvements those are, that might help N2O wise, then that might be an area where you want to go and focus attention to. So that concludes the webinar for this week. Next week, we plan to go through the next step in the journey, which is the monitoring the process and N2O emissions so that we can continuously be reducing and minimizing our N2O emissions. So that'll be next week. Hope to see you, and thank you for joining.